Hi folks, in this video I'm going to talk about several topics, one of them being how to interpret a graph of a function, how to determine whether a graph is in fact a function. Also I'm going to cover domain, range, how to write them, how to understand them in the context of a graph that represents a comparison of two ideas. And so let's go ahead and jump right in. So in this graph here, what I have is an immediate comparison of two ideas. So the first one is age in years versus the number of teens. So it's a comparison of these two ideas. The age in years is our domain. So this represents our domain, and the number of teens represents our range. Okay, so that's our values up and down. Domain is values left and right. So in the first question, we're supposed to explain why the graph represents a function. Now, the way that I like to approach this is there are two ways actually. The most simplest direct way is to do what's called the vertical line test, which is where you take the graph that you have and you draw several vertical lines, and with each vertical line you draw, you're trying to see if your vertical line intersects the graph once or more than one time. So with each vertical line that I drew, you can see that there's an intersection at exactly 1 point along this graph. Every time I drew a blue vertical line, it intersected the black graph only one time. Now what this means is that for every input that I have at this this intersection, so for every input I have, x being here, what that means is that there's only one output, or y, which corresponds with that particular input. In other words, this location, which I think according to the way I drew this would actually be probably 12. So that input of 12 years corresponds to only one total number of teens at the age of, excuse me, this is not 12, pardon me. This would be 13.5. Sorry about that. Make this correction. So this is 13.5 years. So what this means is that for someone who is 13 and a half years old, for this age group, 13 and a half years, there is only one output that corresponds with 13 and a half years, which is the number of teens who have a cell phone. So this would be a little over 229 teenagers who are 13 and a half years old who own a cell phone. There's no other age that has an output with that number of teens who own a cell phone. And the same is true for every other point at which the blue vertical line intersects the black graph. So every input is connected with exactly one output and no other output. And for that reason, this graph represents a function, because the definition of a function is, or whether or not something is a function in this case, is that you have to have a one-to-one correspondence between the input and output. So one input, one unique output. You cannot have, for example, the number 3 as an input. If this were an input, you could not have this input with two different outputs. So for example, you couldn't have this with the number 5 and then the number 7, okay? Because that would represent something that is not an output. Now, the second part of this question is, what is a reasonable domain and range, assuming the data stops after 19 years old? So as I said earlier, the domain represents the age in years, and the range, the number of teens who own a cell phone within that particular age group. So the domain for this would have to be about the ages in years that we are looking at, from the youngest age all the way to the oldest age. And so the youngest age would be 13 years old. That's right over here, 13 years old. So I'm going to put that over here. And the oldest age we're looking at is 19 years. So that would go over here. The idea representing the domain, as I've also stated earlier, is the age in years. So if I were to put that over here, I'm going to get rid of this so it's not in the way. So if I were to put that over here, so the age in years, that represents the idea. Now, some people like to put the corresponding variable. I like to put the idea and mentally connect it with that variable. Domain is always about your x. So just keep that in mind. My x's are about the age in years. Now, because a person can actually be 13 years old, we're going to use less or equal to. And because on the graph, a person can actually be 19, I'll put less or equal. Okay, because you can actually be 13 on this graph. You can see right here. If you're 13 years old, the number of 13-year-olds who own a cell phone in this small town is 229 teens. If you're 19 years old, then in this small town, the number of 19-year-olds with a cell phone is 642 teens with a cell phone. Okay, so that's your domain. The range is about the height of the graph, from its lowest point, absolute minimum, all the way up to its absolute maximum or highest point on the graph. And when I look at this information, this data in the graph, I can see that right over here, that represents our absolute minimum. This is our lowest point. Whereas over here, this represents our absolute maximum. There is no other point that is higher than this point here. The range considers the y values, the outputs. So at the minimum, the absolute minimum, the output is 229 teens. So it's 229 teens. And at its absolute maximum, we have 642 teens. So 642 teens. Now the range is about the number of teens, and I can put that over here. So number of teens. But again, you want to make the mental connection to the typical variable that is about range, and that's the y variable. So range is about y, domain is about x. Now, 229 teens are 13 years old. And so we're going to put less or equal because we actually have this data, this number of teens. There are actually 229 teens at the age of 13 in this small town. And there are actually 642 teens who are 19 years old. So we're going to put less or equal to for that because you actually have 642 people at the age of 19 who own a cell phone. So this is the domain and range for this graph. And that answer is number 1. All right, let's look at question number 2. These following questions are, they're all based on the graph that we were looking at a moment ago, and I'll go back to that. But the question is, in number 2, is a function discrete or is it continuous, and why? Well, in this case, the function itself is a continuous function because one way of thinking about it is that from its beginning to its very end, the graph continues. As you can see, it just continues unbroken from beginning to end. That continuity, the flow from the beginning point to the end point, is what makes this continuous, a continuous function. Discrete would be if there's some kind of a break. So for example, if I were to redraw this, kind of like this, and then there's a break, and then it goes up, down, and it finishes. The fact that there's a gap right over here, this gap would mean that this graph is discrete because it does not flow and continue non-stop from beginning to end. It is broken, and that interruption would make it a discrete function. So this would be discrete versus this being continuous. Okay? Another way of looking at discrete graphs would be if you have a coordinate plane such as this, and you have, as your graph, you have just a series of points that are, sort of splashed onto the coordinate plane, and they're completely disconnected. This would be an example of discrete because there is no continuity from one point to the next. There are separate points, and we look at only those separate individual points depending on what we're analyzing. Okay, so this would also be an example of a discrete graph. So discrete and discrete. Okay, next question. What is the absolute maximum and minimum? Explain what they mean. Well, I kind of already answered that, but I'll be happy to do that again. So the absolute maximum for this would be this point right here. So as I've already said, this is the absolute maximum. And this point is located specifically at 19, because that's the number, that's the age in years. So 19 years old, 19 years, and 642, which is a number of teens who are 19 years old who own a cell phone. So that's the meaning of this point, is the absolute maximum here represents 642 teens who are 19 years old and who own a cell phone in this small town. The absolute minimum would be this point over here, and let me circle that better. This point over here. So this is the absolute minimum, meaning that there's no point on this graph which sits lower than the one I circled. And what this means is that in this small town, there are 229 teenagers aged 13 years old who own a cell phone. So 229 teens at 13 who own a cell phone. That's the absolute minimum. Number 4, what is the relative maximum and minimum, and explain what they mean? Okay, well, relative max and min can sometimes be a little confusing. The relative max is a point that is high, but not as high as the absolute max. Not only that, but it also occurs, the relative min occurs as a switch point. In other words, a point at which the graph's direction changes from increasing to decreasing. So if you follow this graph with your eyes, it's going up, 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 and then it reaches here, and right at this place, it changes direction and it goes down, 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 right? We're going to forget what happens after 530, but it stops at 530. This place, this 590 that you see over here, this is your switch point. That is the relative maximum. It is the place that is not as high as the absolute maximum, which would be 642, but it is also a high point. And not only that, it's a point where the direction of the graph changes from increasing to decreasing. Okay, so this relative max would be at 17, 590. And what this means is that there are 590 teenagers age 17 who own cell phones in this small town. That's what it means. Now, the relative minimum is kind of the opposite idea of the relative maximum. So the relative minimum is a point that is low on the graph, but not as low as the absolute minimum, which would be that one in the blue circle. That's the absolute minimum. The relative minimum is a low point, but it's a low point that is also a switch point. When the graph switches its direction from decreasing to increasing. So if you remember, we went from 590 to 530 and we stopped. Well, if you were to go from 590 to 530 and then go up from 530 to 642, that's a change in your direction or in your slope. You're decreasing and then suddenly you're increasing as soon as you pass that point 18, 530. And so for that reason, this point represents a relative minimum. And this occurs at 18, 530. And what this means is that there are 530 teenagers aged 18 who own cell phones in this small town. All right, covered that. So let's take a look at this now. We're going to switch gears a little bit. In this question here, we have a data table right over here. And what we were supposed to do is base our answers on this data table. So the first question is, what is the equation y of x? So what would this look like if you were to actually complete the function that you see started over here? Well, in order to answer this question, you have to be able to decipher the patterns that are occurring in the table. One way that you can do this is to consider what is being done to each input to produce the output. So every input leads to an output, right? And the way that that the output is created by using the input has to be the same method for any input that you use. So if you're going to add 3 to the input to make the output, well, then you have to add 3 to each input to get your output. Okay, so if you add 3 to any input, it'll give you the correct output. But if it only applies to one line, but it doesn't apply to any other row, then it's not the pattern and you cannot use that. So let's take a look at this. It has to be a consistent, repetitive method that can be used for any line. So let's look at the first line. In the first line over here, I have 0, 3, or 0 as my input and 3 as my output. And excuse me, when I look at this, I look at the number 0 as sort of a beginning point because 0 represents a starting point on the coordinate plane. So when your input is 0, before you've actually done anything, your output's already a 3. And so what that means is if I wanted to make a 0 into a 3, the only way I could do that is by adding 3 to a 0. Right? So I have to add 3 to 0 to make a 3. So 0 and then plus 3 equals 3. Let's see if that works on the second line though. So if I were to take a 1 and add a 3, would I get 5? No, I would get 4. But man, I was supposed to get a 5. I didn't get a 5. I got a 4. So that means that adding 3 to each input will not give the output, the desired output. And that means either of two things. Either we just don't add 3 at all, we throw that idea away, or we have to do something to the input first and then add 3, and that will give us our output. So let's experiment with that idea, because I know that the only way that I can turn a 0 into a 3 is if I were to add a 3. So I know that that's a valid explanation for the first line. So I'm going to leave that plus 3 there. The only other thing I can think of, which is my second option, is that I need to first do something with my input before I add the 3. So let me play around with something here. So if I take my 1 and I think to myself, well, what if I multiply something to 1 first before adding 3 to it? I'm going to erase my 4 there. Let's say I multiply this by, well, 1 and 5 are not too far away, right? 3 plus 1 is already 4. I know that 3 plus, get rid of that. Sorry, I'm just going to try to work backwards here. I know if I'm trying to make a 5, right, and I have something plus 3 makes 5, that's something. The only way to make that something would be to first see what happens when you subtract 3 from 5. So if I were to subtract 3 from the 5, then I get whatever goes in there, it has to be equivalent to a 2. Okay? So, getting rid of this. So if I were to go back over here, right, and I put a 2 in there, Now 2 plus 3 is 5. Yes, 2 plus 3 is 5. But now how do you make a 1 become a 2? How do you make this 1 turn into that necessary 2 so that when you add it to 3, you get the 5? Well, the only way you can make a 1 into a 2 is if you were to multiply the 1 by a 2. Of course, you could add 1 plus 1, but we want to go the route of multiplication here. So if I were to take the 1 and multiply it with a 2, now 2 times 1 is 2, and 2 plus 3 is 5. Huh, interesting. I wonder if I were to go back to my first line and apply that rule, would it work, and would I still get a 3? So let's see, if I were to take a 0 and multiply it to a 2, I would get 0, and then if I add 0 to 3, I get 3. So it seems to work for 2 lines, so this is looking like a pretty valid method, but I have to test it on the 3rd line. So here I go. If I take the 3rd line, if I take my 3rd input, which is a 2, okay? I'm going to take this, drop it in right there. If I multiply it by the 2, and then I add 3 to it, would I get 7? Let's see, 2 times 2 is 4, and 4 plus 3 is 7. So I got it. So in other words, if we remember that all of these numbers inside the parentheses, all of them represent our input or our x, then all I have to do to complete the function is say y of x is to get your output, which is this over here. To get the output, all you have to do is double the input or multiply x by 2, and then you add the 3. And that would be how you get the function. Okay, that's number 1. Bit of a lengthy explanation there. Hope I didn't wear you out by it, but I wanted to give you something to think about. Number 2, if the graph was continuous, what is the domain and range if the input continues to all positive integers? And before I answer that, a thought just popped into my head. Just going back to this, if some of you viewers might be looking at what I did for number 1 and thinking, gee, man, he took a long way around to get to this. I could have answered that real quick by just using getting the slope or using point slope form or something like that. If you know those concepts, then yes, by all means, use them. They work. But this explanation is for individuals who have not yet been exposed to those topics of point slope or slope intercept forms and still have to find a way to complete the function for this data table. It is very possible to do that, as I just demonstrated over here. So just wanted to clear that up. All right, back to number 2. If the graph was continuous, what's the domain and range if the input continues to all positive integers? Well, we're talking about the data from this table. So if the graph was continuous, okay, so that's a key word. This continuity means that, it flows without interruption, okay? This data table is showing us only a portion of the graph. And if I were to continue my inputs here based on this function, then I could essentially get outputs forever, okay? I could get forever outputs. So this would lead to forever outputs. If I put in input after input after input, I would just get forever outputs. So it's asking, what is the domain and range? Well, we also have to consider that this graph here is starting at an input of 0. And although this function could handle values that are negative, we don't have enough information to know if we should consider negative inputs. So I'm going to go with the premise that our inputs have to be whole numbers only, okay? Because we're starting with 0 and then getting more positive from there. So the domain for this, I'm going to go ahead and do this first. I'll bring it over here where I have more space. The domain. The domain for this would start at 0, but because we could possibly go forever in that direction, right? Just keep getting more positive forever. Positives never end. This could go to infinity. Now, domain, as I said earlier, has to do with x, so I'll put that there. 0 is a valid point or a valid value in our table, so I'll put less or equal to. so that we include 0. But infinity is not something we can actually grasp. You can't point to something on the graph and say, oh, there's infinity. It's right there. You can't do that. Infinity is always in motion. So I can only use less than for this. So the range. So the range, or the outputs, which come from the domain or the inputs, my lowest range, or the value that corresponds with my 0, is a 3. That's my lowest value in the range. My highest value would also be infinity, because if your domain is infinite, that means that your input can be limitless, and that means your output can also be limitless. So I also have infinity there. Range is about y. The value of 3 is a valid number in our data table, so we actually have it, so less or equal to, but infinity is elusive, so we put less than, because you cannot actually be equal to infinity. And that's the answer for number 2. Last question, make a graph for the function. Well, from our data table before, we have 0, 3, 1, 5, 2, 7. So 0, 3, 1, 5, 2, 7. These are our input, output relation, right? So this whole thing is a relation, or a set of ordered pairs that belong in the same family. So if I wanted to make a graph for this, then I would have to make my coordinate plane. This is my y-axis. This is my x-axis, and then I go ahead and start dividing it up. So my highest output is 7. So 1, 2, 3, 4, 5, 6, 7. And my greatest input is just a 2. So 1, 2. So from this, here is roughly what the graph would look like. So 0, 3 would be right here. That's 0, 3. 1, 5 would be up here. 1, 5, and then 2, 7 would be way at the top, which is over here. That's 2, 7. So first thing that you should note is that that these things actually do form a line, and they should, because this function that we had earlier, this y of this y of x. Y of x is equal to 2x plus 3. This thing here represents a function that has no limits, right? So, and it does represent what's called a linear function, which is, in graphical terms, it's simply a graph of a line. Now this line, again, as far as we know, starts at 0. We don't know, we're not told enough about whether or not we are allowed to go negative. So I'm going to start my graph here. Oops, sorry about that. Try this again. All right, so we're going to go there, and we're going to go all the way up. And then, when we remove the ruler, put an arrow on it. And that arrow, again, indicates that our domain and our range are infinite in their own respective directions. So I'm going to highlight the points that I had. These are the points that I had earlier. Okay. All right, and that is number 3. Number 4. So number 4 is saying, all right, so what would y be? What would your output be if your input is 15? So this over here is asking, what is the output if your input is 15? Now we have our function. I'll write it over here again. Our function is f of x, or I should say y of x, just to be consistent, is equal to 2x plus 3. Well, if our input is 15, then I have y of 15 is equal to 2 times 15 plus 3. 2 times 15 is 30, so now I have 30 plus 3, and that would give me 33, and that would be my output. Okay? So y of 15 is equal to 33. So I hope this video helped you to better understand domain and range, how to write it, how to pull information from a graph, how to understand evaluating a function, how to create a function from a table, and how to decipher the patterns that lie in a table. A lot of information here, so please stop by, leave a comment if you like. Tell me if this worked for you, or if you think something could have been improved, or if you think I made a mistake. I'll do my best to reply in a timely manner. And as always, thanks so much for watching. Bye-bye.